So welcome everyone. My name is Aurelio Muraca. I am the Technology Program Coordinator here at the Danbury Library. And welcome for this, again, Series 3 of Earth in Crisis with Dr. Mitch Wagener of Western Connecticut State University. And tonight we'll be talking about green hydrogen and other things as well. So without further ado, Dr. Mitch, thank you for joining us again this evening.
Thank you for turning out. It's always I always enjoy doing these. First of all, let me mention that come March, we're going to have 5 weekly in-person talks, the Jane Goodall Climate Series, and I'll make sure that Aurelio has the schedule for that. And these are faculty members collaborating with students to present a particular topic on climate change. I'm going to do 2 of them because we were missing a speaker. So I'm going to do fire ecology, which I've probably done here for you at Danbury. If not, I can easily do it. And collaborating with a student on climate hope. Always important thing to include in this discussion. Where this is climate change in general is a topic that's fraught emotionally, and so one has to discuss it wisely, and I try my best to do that. This is our science building. I always use this as my opening screen because I'm hoping that there may be people who are interested in taking classes and coming to Western to do so. Oh, well, okay. Now, at some point in the evening, my wife is going to come through the back door behind me coming home from work. My dog is sitting in my lap. So that's the scene here. If we look up in the night sky on a nice warm day or a warm night, you see all these beautiful specks of light. And what we are seeing, if you don't remember your college physics, if you never took college physics, what we're seeing is the results of hydrogen energy of a sort. Okay, hydrogen can be used in a couple of different ways. You can have hydrogen gas, which you then burn in a simpler, complicated form to generate heat and run pistons and generate electricity and things like that. Potentially, we may someday find a way to harness fusion, which is the energy of the stars, which is another form of hydrogen energy. And what we see in the stars is the same thing we see in our own star on a nice sunny day, and that is vast amounts of energy which are being released by the fusion of deuterium and tritium. More on that in a bit. Well, let's see here. So just to set the ooh-ah scene of here, each galaxy contains, oh, by the way, these are not all stars. Some of them are galaxies. Collections of stars like our Milky Way. So there's even more going on in this picture than one might think if you saw each one of these as stars. With that new telescope that NASA has up, we can see an awful lot more detail than we were able to in the past. Okay, so each galaxy contains 10 to the 7th to 10 to the 14th stars. That's 10 with all those zeros. And there are 170 gazillion, I don't know how many galaxies in the visible universe. So you can kind of do the math and figure out how many stars there are just in that part of the galaxy or universe that we can actually see, which is, who knows, we assume it's a small part of that. Now, let me remind you of your chemistry. Within the chemical table of elements, there are a number of them that we interact with generally quite often hydrogen is the smallest of the elements. Oxygen is the one we need for metabolism. Carbon makes us up, and so on. We have and use a number of these in our bodies, but also in our civilization. Now, let's talk about hydrogen. One of the things is, being the smallest of the elements, the best way to get the most energy out of hydrogen, if one could do it safely, is by slamming individual hydrogen isotopes together to form helium, which is exactly what the star does. Our star and the other stars do, insofar as we know. One of the loveliest of the photographs, and this is from Hubble, the older telescope, showing a cloudy formation, which is what's called a star nursery, where the hydrogen in the form of stars comes together and collects into large enough bits that you can make a decent mid-Italy night and make a star from it. It does look like an animal standing up on its hind legs, but that's just a function of the angle at which we're looking at it. Now, if you remember your college chemistry or high school chemistry, perhaps, you know that elements can have different forms. They're called isotopes. And the most common of isotope of hydrogen is the smallest one, that contains one proton in the middle, in the nucleus, with an electron around it. There are two other forms. There's deuterium and tritium. And deuterium is it has twice the mass, has two objects within the nucleus and an electron, and then tritium has three. Now, the way radioactivity works is that a parent isotope will convert into a radioactive isotope, which will then break apart. And this is the type of nuclear energy which we can and do harness, although not perfectly, that allows us to heat water and generate electricity. It's called fission. Fission is where a larger molecule is broken apart to form small molecules, smaller isotopes of different elements, and radioactive energy is released. Okay. That will generate a significant amount of energy, but the one, and in the example that is often the one we use a lot for fission energy, is uranium-235 turning into uranium-236, which then breaks apart into krypton and barium. Let's see. Now, the real energy, however, is in not fission, breaking apart a big atom into, but small atoms that slam together. Okay, and as I mentioned before, if you take a deuterium and a heavier isotope of hydrogen and tritium, and even heavier isotope, slam them together with a huge amount of force, as happens within the gravity of the sun, it forms a helium and a neutron, a spare neutron, and lots of energy. Okay, this is the energy of the suns. It's also the energy of the H-bomb. This is how H-bombs generate the massive power that they use, and may they never be used on people. This one, by the way, I believe is Tsar Bomba, the Soviets' largest fusion bomb ever exploded, that they did as a big publicity stunt back in the early 60s. The pilot of the plane that delivered the bomb did not survive. Sodawomba, by the way, means the emperor of bombs. So getting back to our sun, our little pedestrian sun, which is middle of the road in size and energy and all that sort of stuff, but it is ours, and it gets its energy from that. At some point in early the life of the star, there will be the collective gravity will pull enough deuterium and tritium together that it reaches critical mass and can ignite. And at that point, it is gradually converting itself into helium. And stars also have a time when they fade out and lose the ability to generate a lot of energy. Ours has got a long ways to go before that happens. So don't worry about it. You have plenty of of time before we have to worry about that. The stars also have lots of other things besides just hydrogen. They have all sorts of other elements, metals, and all sorts of things, which can be observed from a distance. We can, looking at the spectrum emitted by stars that are quite far away, get a pretty good idea of the kind of things that are in that star, along with how big it is and how old it is and all that sort of stuff. And that has been being done for many decades. Our star is pretty much middle of the road. Now, the sun has always been observed and respected and revered by human civilizations and cultures around. After all, why wouldn't you see it as a special thing and perhaps a supernatural thing when it is what brings you warmth and brings you the ability to grow crops and all that sort of stuff. And different cultures described it and understood it in different ways. The ancient Egyptians had a couple different ways of looking at the sun. In some cases, it was associated with an asp and associated with the god Horus, the one that had the falcon head. The Egyptians also put some consideration of how the heck the sun will set in one spot of the sky, one horizon, and then appear in more or less the direct opposite horizon the next morning. How is it that the sun pulls that trick off? Well, I mean, that's a reasonable thing to consider. And the story that the ancient Egyptians came up with was a very large dung beetle would roll the sun, would take over its care and roll the sun from the western horizon to the eastern horizon over the course of the night. And the dung beetles had a very important place in the cosmology and spiritual beliefs of the ancient Egyptians. It was also where one's soul could be found. And so those who had the money to afford a cartouche could have a lovely dung beetle inspired object placed on their chest of their mummy for all eternity as the place where the soul would reside. The average bloke on the street didn't really have that opportunity. So now, at some point, the ancient Egyptians, a particular king, Akhenaten, to be exact, who was King Tut's father, decided that he was going to change or reform the religion of the ancient Egyptians and making it a monotheistic religion with the god the god that they would accept represented by the sun in the sky, Aten. And here is that particular pharaoh, his wife, and several of the kids. and he suppressed the other ancient belief system, as often happens. But when Akhenaten died, his sons threw out Atenism, his religion, and replaced it with the old ways. So that didn't last very long. The Roman and Greek civilizations saw the sun being pulled by Helios and his chariot pulled by 4 horses. And the Helios was seen as a symbol of the sun, and the sun was seen as a symbol of eternity. And so the Romans made a big deal about trying to associate Rome, the Roman Empire, with Sol Invictus. This is this is actually Constantine, which is kind of ironic since he did not keep the pagan ways his whole life. Anyway, this is a coin of Constantine, I believe. And on the reverse, on the left, you see Sol Invictus, the unconquered sun, the notion that the sun is a symbol of the eternal future of the Roman Empire, which of course, empires are never eternal. Now, the sun has all sorts of things going on that can affect us directly and indirectly. The sun has its own magnetosphere, and so that it actually will have storms. It's not a object which is constant. It has its little conniption fits every so often. And solar flares are something that occurs fairly frequently. And, there's several per day when the sun is particularly active, and less than one a week when the sun is quiet. And since they are controlled by the magnetosphere, they tend to be, when looked at on the side, a loop where the energy goes up one side of the loop and down the other. Whoops, sorry, my dog. I can move the slide back. Sunspots were something the ancient Chinese astronomers discovered, not by looking at the sun directly, but by making pinhole cameras with paper, which you can still do today. And they saw that the sun has some schmutz on it, some little bits of gunk that look like dirt on a lens. And we didn't find out until much later that those were indications of storms, and the little dark spots were the cool spots, a mere 3,000 to 4,000 kelvins, surrounded by a hot area that was over 5,700 kelvins, and quite large. So the ancient Chinese first discovered them in 28 BC, and they began to record them systematically in the 12th century. And they look like this if you were to look at them in a safe way. And so it does look like just some dust on the lens. Now, this one is important for human life, and it's important for our use of energy going forward, and that is the solar wind. The sun emits not only just light, not only just electromagnetic radiation, but particles as well. Bits and pieces, charged ions, and subatomic particles like electrons and protons who are streaming away from the sun and all time. And they have effect on things. Now, if you've ever seen a comet, I remember back in 80, whenever it was, 85, when Halley's comet made its most recent trip through here. I was living in Belize at the time and went out and stood on the beach with my binoculars and saw Halley's comet. It was kind of dim, but I saw it. And, we associate comets with a tail, having a tail. And they are balls of ice and dust that spend most of the time way the heck out past the Oort cloud, way past the planets and other things that are they're sometimes, seen in telescopes. And every once in a while, one of them will get joggled by some gravity well and get pushed to move down towards the sun. As they reach the sun, they warm up and the water vapor outgasses, and it is swept away along with the dust. And the tail is not pointing the way away from it is not pointing the way that the comet has come. It's pointing away from the sun. So when the comet is moving toward the sun, you've got it moving just the way you would expect from what it looks like, with the ball, the main part of the comet, in the fore, and the tail in the back. Well, when it rounds the sun and starts heading back the other direction, it's moving tail first, because the solar wind is pushing that away from the rest of the comet. So it's moving backwards from the way one would expect from looking at it. Of course, they don't move very fast. Anyway, the solar wind's also important because at some point, Mars, the planet, lost its magnetic sphere, or most of it, and that's because it cooled faster than the Earth did. And so there wasn't anything there to protect the atmosphere from the solar wind, and the solar wind swept most of it away. And so here's our comet, and this one, you can't tell which way it's moving from this picture, but you can tell that the Earth, or the sun, is somewhere to the bottom and to the right. Now, the other thing, the biggest storms are called coronal mass ejections, and sometimes those things just unluckily get sent toward Earth, and that cause disruption of electronics and things like that. All right. Now, we are protected by the fact that the Earth is still hot on the inside. It's hot on the inside, and that heat is residual from the formation of the Earth all those many gazillion years ago. It has cooled from the outside, and it's still hot in the center. That means the consistency of the core is different than the rest of the Earth. And so when the Earth spins, the core spins as well, but at a different rate. And so put the two together, and you have an you have a magnetic sphere generator, which puts this protective shield around the Earth, and it protects our DNA, but also our atmosphere. The reason why we have it and Mars doesn't is that Mars cooled off faster because it's smaller and farther from the sun. All right. There has been much effort and no small amount of money, to try to figure out how we can harness fusion for electrical power generation. Can't say it will never happen, but it hasn't so far, because always let me back up and see, the research into fusion reactors began in the 1940s. We have had bombs, hydrogen bombs, for a long time, but bombs by definition are not controlled reactions. You just set them off, boom. Okay. In order to harness the energy and actually turn it into electricity, we need to control it. And therein lies the rub. There is so much energy released from fusion that you have to put so much energy into controlling it that we do not yet have a system of doing it where we don't use more electricity to control the reaction than we get out of it. Doesn't mean it won't happen, but it hasn't yet. Okay. Proposed fusion reactions generally use a mix of deuterium and tritium, like the sun does. And most designs aim to heat their fuel to around 100 million degrees, which requires confinement and lots of fail-safes. One cannot describe how important it is to not let one of these things go critical. And so there's a huge amount of wiring and power that needs to go into building a magnetic sphere around the thing to keep it from destruction. Now, I remember in 1989, there was much to do about the announcement of two electrochemists named Martin Fleischmann and Stanley Pons, that they reported that they had an apparatus that would produce excess heat at room temperature of a magnitude that they asserted would defy explanation except in terms of nuclear processes. They claimed to have cold fusion. I don't know if any of the rest of you were in the science world and heard all of the hubbub about it. And it was also called a fusion martini. It was something that they held up as this piece of glassware with wires coming out of it. And they said that they got readings from it, from their tests, that said that more energy was coming out of it in terms of heat than energy put into keeping it stable, because that's what has to happen before fusion is a possibility for a energy source. But no one could repeat their results, and neither could they. Okay, so that's where it stands. The fusion martini probably had spurious results. Fleischmann and Pons probably got overly excited because they got something that looked like it was positive energy output, but it probably wasn't. Okay, so that's one possible way of generating energy from fusion, is figuring out a way to do it at room temperature that does not go boom. Okay, that does not require so much energy to maintain it. The way we can get energy from hydrogen, and in a way that is controllable, is through chemistry rather than from nuclear physics. By the way, I'm a biologist and ecologist by training, so if any of you are physics, and if you ask me about physics, I may not be able to answer the question, just to let you know. But if I can't, I'll tell you I can't. So anytime that you get some diatomic hydrogen and oxygen and you put a light to it, you get water and you get heat. Okay, so if one could manufacture hydrogen, which is generally done through the hydrolysis of water, you take water and you run some electricity through it with electrodes of a particular metal, and it separates the water into hydrogen and oxygen, which is what you get when you then take those gases and burn them. Okay, we've known how to do this a long time, and we've been able to produce quite a bit of hydrogen. You may remember this one, the Hindenburg, which at that time of early airships, the Germans had put a lot of effort into the technology of airships, lighter than aircraft, but they were having to use hydrogen because the US was sitting on the biggest supply of helium at the time. Helium will not go boom. Helium is an inert gas and doesn't react chemically, and so you can safely use it for a dirigible or a Zeppelin in this case, where you can't do that with hydrogen. And this thing landed in New Jersey, and apparently a spark came off the tower or something that ignited the hydrogen, and it was quite spectacular. But it also gave us a really cool album cover for Led Zeppelin. So there you go. So how do you make hydrogen? Well, you take water and you run electrical current through it. It's called electrolysis. It's simple, it's easy, but you put more electricity into it than the energy you get out of it. Another way to do it is through a hydrogen fuel cell, which is more complex. It's a system that is fairly common for large scale uses. In the science building in Midtown campus, there is a hydrogen fuel cell. I think this one's a hydrogen fuel cell. They just replaced the fuel cell. And I haven't been back there to look and see if it's the same, but the previous one was a hydrogen fuel cell, and that we had for some years, and it generated electricity for our science building. And so what I'm going to tell you is about the old one. I don't know if the new one is quite the same. All right, a fuel cell is an electrochemical cell that converts chemical energy of a fuel, often hydrogen, into an oxidizing agent, often oxygen, into an electricity through redox reactions. Okay, controlled mechanism of generating power. Fuel cells require a continuous source of fuel and oxygen to sustain the chemical reaction. In a battery, the chemical and energy usually comes from substances that are already present in the battery. In a fuel cell, you're making the energy for the battery as you go along. Okay. Now, there are fuel cell cars, at least in prototype. I don't know if there are any operating models that you can get, perhaps there are, that have an electrical motor, a power control unit, a battery, and a fuel cell that that generates electricity from hydrogen and oxygen. Now, the thing that we have to ask ourselves is, where's the hydrogen coming from? Is hydrogen green? Depends on where the electricity comes from to make the hydrogen. Okay, now here's our former fuel cells. Okay, they were very good. The company was to put instructions on how it all worked, and I'll explain the basics to you. I have to get out there and look at the new one and see if they have that kind of information. I suspect it's probably a updated version of that. Okay, so it's a natural gas fuel cell. Natural gas is piped in, and this is the natural gas where it comes in and is attached to the fuel cell. How does a fuel cell work? Well, there's a schematic showing us how it works. And basically, it happens like this. First, natural gas, which is mostly methane, comes in. The steam is used to reform the methane into hydrogen-rich gas. It's an intermediary. Okay. The steam comes from process later. Okay. This is a clean, then, according to the description, the clean exhaust is vented. They don't say what's in the clean exhaust. Catalytic reaction converts hydrogen to protons and electrons. The electrons flow through the circuit and produce electricity. Electrons, protons, and water, or and oxygen, form water, which becomes the steam heated by the process for step 2. And then the useful net heat is produced. So from methane, we are generating an internal cycle of heating and electricity, which is an efficient source of electricity from a fossil fuel. So the questions are, what is the hydrogen-rich gas in step 2? Okay. And where does the carbon go? Okay. So methane is CH4, and you're converting that into hydrogen gas and stuff, but where did the carbon go? And so that is a question that isn't answered on the schematic that I looked at. Well, the hydrogen-rich gas is probably CO2 and hydrogen itself. Where does the carbon go? Probably CO2 released when the clean exhaust, quote unquote, is vented. Okay. So now this fuel cell seemed to be quite an efficient way, perhaps an improvement on gas-fired boilers and things like that. But it isn't the hydrogen, clean hydrogen, green hydrogen that we are still dreaming of. So steam reforming, globally, almost 50% of hydrogen is produced through steam reforming, using steam to heat methane, to gain hydrogen gas, which is then burnt to heat the steam. It's currently the least expensive method for hydrogen production available in terms of its capital costs, as of a couple years ago. So the question is hydrogen green? The answer is that depends on the source of electricity used to produce the hydrogen. If you use a coal plant to generate electricity, and that electricity to conduct hydrolysis on water to get hydrogen, then it's hard for me to call that green hydrogen. Should we find a different way to do it, a more efficient way that doesn't produce carbon emissions, then that would be a truly green hydrogen, and perhaps someday, but we're not there yet, from my understanding. So, can I answer questions? And given that I am a climate change educator and an ecologist and not an engineer or a physicist, but if I can't answer the question, I'll tell you I can't.
Yeah, if you have any questions, please type them in the chat. Take your time. I know this is a lot to process.
It's a lot to express.
Yeah, it is. Here's one. Or do you think we'll be able to achieve, um, you know, green hydrogen, with especially here in Danbury with fuel cell, that company here. Will that happen before we have solar power or some sort of other, alternative energy?
um,
I know it's kind of
I
always,
don't know. I think it may be a asymptote towards something that's better. And will we ever reach, what's truly green in hydrogen? I don't know. I suppose that if you had a mechanism which was renewable electricity from solar, from wind, from tidal, whatever, and you use that electricity to hydrolyze water into hydrogen and oxygen, that you could have something that is green.
mm,
I think I don't want to at all criticize the fuel cell industry, because theirs is a righteous cause. They're trying to do better. They're trying to get better energy with less carbon emissions. So I applaud their efforts. So I don't want to seem like, if any of you all are listening to me, don't think that I'm criticizing you.
yeah, it's one of those things that I was thinking about, if will we ever see cars, run on hydrogen within our lifetime in the
I
next
think that
20, 30.
there are those hydrogen, at least in schematic, there are hydrogen um, fuel cell cars, but the trick is, how do you make the hydrogen? And So there's gonna have to be some mechanism for making green hydrogen before we can burn green hydrogen.
Yeah.
And it may come. I hope it does. But we're not there yet.
Again, if you have any questions, please type it in the chat. We do have, just wanted to let everyone know, like with all of Dr. Wagner's presentations, they will be uploaded at some point, either tomorrow or the next day, onto the Danbury Library's YouTube channel, and I'll be happy to send a link to you all with that, with tonight's presentation. And you can also see the previous presentations on the YouTube channel for the Danbury Library. And we will also send you a survey link in regards to our 5-year strategic plan here at the Danbury Library. And if we want to see more programs like this, more programs like focusing on, environmental issues, green energy, climate change, all that stuff, we're happy to only provide these types of programs to you. So we have some questions now. What are some examples of fuel cell usage today, Dr. Wagner?
Well, I believe that, the scale of fuel cells that we have attached, running the science building is a scale that is, something that we're seeing. I don't know if there's anything larger than that. Perhaps there is. Again, you just have to figure out how to make the hydrogen. There was another one that I wanted to answer. Let's see.
Yeah, go ahead.
Are any countries using alternative energy day to day other than solar? Well, there is a very fortunate island nation in the North Atlantic called Iceland that is sitting on the Mid-Atlantic Ridge that has tons and tons of geothermal, and they are fortunate enough that they have a good source of hot water already coming from the ground. And as I understand it, they are about as green as anybody. It's not something that we can do in Connecticut, geothermal. But I look forward to visiting Iceland someday and taking a tour of all that. Let's see, where's the money come to funding the research? It probably comes from a variety of areas. Some of it can come from the National Science Foundation and various sources of nonprofit research support. Probably there's some industry money in there as well. I don't want to poo-poo industrial support because if something good comes of this, they're the ones that would have the ability to roll this out quicker than just about anyone. Although they're not always as fastidious as I would wish. But I think it's coming from a variety of places. I don't know any more details than that, however. Let's see, have I missed any more?
No, I don't believe so. Anyone else have any other questions for this evening? Otherwise, we'll break early.
Am I early?
Yeah, well, by 10 minutes is fine.
Okay, all right.
Oh, here we go. Are you familiar with the contraption that was built on the Rizzo property?
No, I don't. What, can someone describe it? Is the Rizzo property a family estate of some sort? That sounds like it.
It's on
On
Triangle.
Triangle Street. I
Yeah.
don't know. if there are articles about it, I'd be delighted if someone could send them to me, because I would, if it's relevant to this, I'd like to learn about it. Okay, Honda will introduce a fuel cell CRV in California in March per car and driver. Well, I certainly look into that. I lease a Honda, and I'm in a year and a half or so I'll be trading, returning it to get something new. And I was trying to think about what I could do, whether I should go all electric or hybrid of some sort. But the trick is, if you had a fuel cell CRV here, you also have to have a gas station or some other source that would sell you the hydrogen. Unless you could cook at your own at some point. Which is probably why they're starting it in California. Maybe they have the infrastructure already out there, and trying to work the bugs out, so to speak.
So if no one else has any other questions, I thank you for joining us this evening. And again, thank you so much, uh, Dr. Wagner, for continuing sharing your expertise and your knowledge with us during this Earth in Crisis series. And be sure to look out for our my follow-up email in regards to the upload of tonight's presentation, as well as the survey link for the library. And be sure to check out other programs that we have here at the Danbury Library. And also that link that you could send to me, Dr. Wagner, so I can share to everyone in regards to the Jane Goodall
Okay.
talks and everything.
I have
So
I'm still waiting on a couple of titles, and as soon as I have those all put together, I'll send it to you.
excellent. And I'll be sure to forward that to everyone who has registered for this series and other series. And be sure to register for the next episode 3 end of March. So the link should be up and you'll be able to register right now. So again, thank you. Have a great evening. Until March, good night.